Okay, so welcome back, everybody. Now it's I guess due to some unfortunate circumstances for Rita Pardini, she was not able to give her talk. So we'd like to thank Marco very much for taking over, and so Marco will be giving Rita's talk on deformations of semi-smooth varieties. So thank you, Marco.
So, yeah, I'm here on behalf of Rita Pardini, and first of all, I want to apologize if some part of the talk will be not so precise or some other part of the talk will be too technical. So I'm going to give you some ideas of our approach of studying deformation of semi-smooth variety. So I'm talking about joint work with Barbara Fantechi, and the aim of the talk is to give an explicit description of the tangent sheaf and of the first Schlesinger sheaf T1 of X for semi-smooth varieties. So let me give an outline of the talk. So I will start with our motivation. Then I will talk about general results about smoothability. Then I will explain what does it mean semi-smooth variety. And then I will talk about these main sheaves for semi-smooth varieties and how to compute them. And finally, I will give application to Godeaux surface. So let me start with the motivation. The motivation is the analysis of the deformation theory for certain classes of stable Godeaux surfaces. Well, we work on Godeaux surfaces with Zonke and Rita, and we gave a classification, and most of such surfaces were smoothable, but there are other which we didn't know. So, and this is the main class of such surfaces which we didn't know if they were smoothable. So let me start by describe our construction. So we consider a smooth elliptic curve, and we could take the symmetric power of such smooth elliptic curve, x bar as 2 of E, and we take a trisection of the Albanese map. Okay, this means D bar is a curve such that D square is equal to 3. And we assume there exists an involution on D bar such that D, which is equal to D bar over tau, is a smooth curve of genus 1, an elliptic curve. That means that we have what we call the 2-3 elliptic configuration. We have our D bar, which is of genus 2, and we have a map 2 to 1 onto D and a map 3 to 1 onto E. And we build X gluing X bar along D via our involution tau. That means that we have such push out diagram. We have our map D bar onto D here, and we have the inclusion of the bar into X bar, and then we build X simply gluing X bar along D bar via the map of D bar onto D. It turns out that X is a stable surface with kx square equal 1, pg equal q equal 0, which is a stable Godeaux surface. we have X bar on top X is the normalization map. D bar and D correspond to the conductor ideal. And moreover, as in the classical case, we have the fundamental group is Z over N with N less than or equal to phi. So the question is such an X smoothable? With Zunke, we proved that for N greater than or equal to 3, they are smoothable. And we use arguments very similar to the arguments I showed in the previous talk. So we studied the canonical ring using paracanonical system, just essentially copying the way Miles Reed did. But for N less than or equal to 2, it is not enough to see the way in this way. So we need deformation theory. So now I'm going to talk about general results about smoothability. The relevant sheaves that we are considered are the tangent sheaf, which is home over X of omega 1x of X, and the first Schlesinger sheaf, T1 of X, which is X1 of omega 1x of X. The starting point of this analysis is the result of Friedman from 1983. And Mark Green talked about Friedman necessary condition in his talk. So if we consider X an absolute normal crossing variety, and if we consider the intersection, the I, which is XY intersect with the other component, and we consider the singular part of X, call it D, then necessary condition for smoothability of X is OD of X is isomorphic of OD, where OD of X means the infinitesimal normal bundle of D into X. It is worth to remark that such infinitesimal normal bundle is nothing but our sheaf T1 of X. So a necessary condition is this isomorphism in this case. Moreover, Friedman proved that if we have a global deformation of such an X, such that the Kodaira-Spencer class generates T1X, then Carly X is smooth near X, which means that we have a smoothability condition for our original X. Okay, so this is the story. In a more recent paper, Ciolas proved the following theorem, which says that we have X, a proper reduced scheme, such that X has local complete intersection singularities, and H2 of the tangent sheaf is 0, and H1 of the first Schlesinger sheaf is 0, and moreover, T1 such sheaf is finitely generated by global section, then X is formally smoothable. What does it mean for formally smoothable? I don't want to enter into details, but this means that we have a formal deformation, which essentially means that we consider the formal affine spectrum instead of the spectrum, and we have a condition on smoothability over X bar, which may be written using the fitting ideal. And this means a formal deformation. I don't want to enter into details because we need effective deformation. We work in the category of algebraic varieties. And it is helpful, the following results, which probably is well known to experts. So, but we did not find a suitable reference. Likely, a student of Barbara Fantechi in his PhD thesis was able to find these results, which means that if we have a projective, pure reduced scheme with locally complete intersection singularities and kx or minus kx ample, then being formally smoothable is the same of being smoothable. So we use these two results of Nobile and Ciolas as a black box. And we are going to find a way to compute the tangent sheaf and the T1 of x, keeping in mind this result. Okay? Okay, so we were interested in semi-smooth varieties. What is a semi-smooth variety? A semi-smooth varieties, let me consider first the case of surface, which means that we have X, a smooth surface with D, the double locus, and double locus is locally or a double crossing or a pinch point. And we consider the normalization X bar. So this is a semi-smooth varieties, which on one hand can be seen as X with a double locus, and on the other hand, X bar with D bar, having a map onto D. The map from D bar onto D is 2 to 1, and we have these embedded points, which corresponds to pinch points. We may generalize this construction in any dimension as follows. So an n-dimensional variety X is called semi-smooth if locally X is isomorphic to the spec K of K, or well, in this case, we are working over C, but most of our results work in characteristic different from 2. So we have this pinch point surface cross AN minus 2. The point, the locus where X is equal to Y, it's equal to Z equals 0 correspond to pinch points. And where Z is different from 0, we have double crossing points. Such surface, such variety in general, were studied in detail by Ferran in 23 in a more general context. Our proposition is the following: quasi-projective variety X is semi-smooth if and only if X can be built via X bar smooth and D bar a smooth divisor contained in X bar, and a map 2 to 1 onto a smooth divisor D, such that we can obtain X as a push-out scheme of X bar glued along D bar with D. So we have here, this is X bar. So we can build X in this way. So, and we write X in the following: X bar union glued along the bar with D. We have, remember, X bar is smooth. The bar in X bar is a smooth divisor, and we have an involution such that the quotient via this involution is smooth. And now let me call the map of X bar to X F, which correspond to the normalization of X, and G, the map from D bar to D. G is a flat double cover. So we have G lowest star of OD bar can be written as OD plus L minus 1, where L minus 1 is an invertible sheaf such that 2 times L is linearly equivalent to a branch locus B. So now I am describing how to see the tangent sheaf and the first Schlesinger sheaf for a semi-smooth varieties. So we have F from X bar to X. First of all, we have an injective map from tau or from tangent sheaf of X to F lowest star of the tangent sheaf of T X bar. And we set G equal to co-curl of alpha. The first theorem we have is the following description of G. G can be seen as the co-kernel of the following map of sheaves. So we have G lowest star of the tangent sheaves of D bar invariant, which means invariant part of G lowest star of T D bar with respect to the involution given by tau. Then we have G lowest star of the tangent sheaf of X bar restricted to D bar, and then we obtain G. That is, we have this following a couple of exact sequence, which is helpful to consider our tangent sheaf. Okay, what is the idea of the proof? The idea of the proof is quite simple. We have Tx bar is isomorphic to f up star of omega x dual. This is the first part. Then we have that the map f lowest star of Tx bar into G factors via G lowest star of Tx bar restricted to the bar. And then we take local coordinates. For simplicity, I show you in dimension 2. So locally x bar is given as A2 with coordinate xy, and x is described as a locus given by the pinch point. And the map is given simply xy maps to xy, y, x square. So that D is given by u equal v equals 0, and the bar is given by y equals 0. And with this map, we can compute in local coordinates taking derivatives, and we have the results of the theorem. I want to remember that D is the reduced part of the singular locus. We have the embedded points given by the pinch point inside the singular part. And we have the following construction. Okay, the bar and D corresponds to the skins defined by the conductor ideal. And we have G, which maps D bar onto D, and F, which is the normalization map. First of all, the first observation is that the T1 of X is an invertible sheaf on X singular. And we have an exact sequence as follows. We have T1 of X maps onto its restriction to the divisor D. And we have a kernel given by I of D restricted to X. Simply this way. So now we are going to study T1 of X using this fact. So we have the map from D bar onto D is a 2-to-1 map, and we have G lowest star of OD bar is OD plus L minus 1, where B is the branch divisor. So we set R equal to G minus 1 of B, which is contained in D bar. And we have a restriction map of G restricted to R, which gives an isomorphism to B. So now consider the normal bundle of D bar in X and tau our involution. So the second theorem is the following. So first of all, we have the part restricted to D. So we have T1 of X restricted to D is isomorphic to all tensor, the determinant of the G lowest star of the normal bundle minus 1, everything to the minus 1. And the second item is that if we pull back on X bar, T1 of X restricted to D, we obtain G upper star of L square tensor to the normal bundle of D bar in X bar tensor to tau star of the normal bundle. So we have these three pieces. And finally, the ideal of D inside the singular locus of X can be seen as the push forward via R of the normal bundle, the inverse of the normal bundle restricted to R. So it's quite complicated, quite technical, but it is the way to construct. What is the idea of the proof? The idea of the proof is the following. We take X0 bar, the total space of the normal bundle of D bar in X bar. And we may see the bar as the zero section of the normal bundle. So now we consider a new variety. X0 is given as X0 bar glued along the map from D bar onto D. So we glue this time the normal bundle. The key point is that there exists a degeneration as follows. So we have from one side, we have our X0 just built, and on the other side, we have our X cross U. And in the middle, we have this X curly. So we have D is the same, the bar is the same. So we have D cross A1, which maps into X bar, maps onto 1. And from one side, we have our X on the right. And on the left, we have X0. And the key point is that T1 of X0 restricted to D is isomorphic to T1 of X restricted to D. This is the key point. How can we see this? This follow just considering what is called the degeneration to the normal bundle. Sometimes it is called degeneration to the normal cone. Plus a result about base change for X. Indeed, we have the following description. We have D cross A1 is nothing but the singular part, the reduced singular part of curly X. And we have this base change result. X1 of omega Q, Q is the map of OX curly X restricted to XT is nothing but T1 of XT. In particular, we obtain that T1 of XT is constant. Here I have put under the carpet the hard part of our paper. This base change result is based on a deep analysis by a derived category. And Barbara is an expert, so we use the cotangent complex and all these kind of arguments to prove these isomorphisms. So once that we have this isomorphism, the second part is to build this normal bundle and to study the normal bundle and to see the normal sheaf of the bar. So we consider E equal G log star of the inverse of the normal bundle of the bar into X bar, which is rank 2 bundle. And we have X0 can be seen as a divisor inside the total space of this bundle. In such a way that the T1 of X0 restricted to D is isomorphic to O of X0 restricted to D, to the O of the total space. We have Q from our total space onto D the projection, and this O of the total space of this X0 is isomorphic to Q up star of L tensor the determinant of E to the -1. So this is the key point. So the first point of the proof is to use the degeneration to the normal cone or the normal bundle. The second part is to consider the situation where we have the normal bundle and to compute it in local coordinate and see this kind of isomorphism. So it is not so easy, it's quite difficult to describe. But those are the two ingredients for the proof. So finally, I want to give you the application to Godeaux surfaces. So let's go back to our original motivation. So we have X bar, which is S2 of E, and we have a map onto E, and we have an involution of the bar, which is a trisection of genus 2, which maps onto D, which is smooth elliptic. So we consider our X as a push-out surface obtained gluing the bar along D. And what we obtain is the following: that we obtain that X is mutable. And how can we prove it? We can prove it applying Ciola's theorem plus our description of the tangent sheaf and T1 of X. In which way? In the following way. So we have to prove the condition of Ciola's. First, we need to see H1 of T1X equals 0 and T1X globally generated. But this is quite easier to see, because from this exact sequence, we have that T1 of X restricted to D on this part. It's a positive degree invertible sheaf on an elliptic curve, while the kernel is supported on points. So it's easier to see that the vanishing of H1 follows from the vanishing of H1 here, and as well as the being globally generated. And to prove that H2 of T of X equals 0 follows from, first of all, our exact sequence with the definition of G. And we have that H2 of F lowest star of Tx bar is equal 0 since it is 0 on X bar. So it is sufficient to prove that H1 of G is equal to 0. And we consider with this aim the second exact sequence, which means that we have G lowest star of T of the tangent shift to D bar invariant part, and G lowest star of the restriction of the global tangent shift of X bar to D bar into G. And we take cohomology, and we have this exact sequence and this isomorphism. We have H1 of G is isomorphic to the normal bundle of D bar into X bar. We have this isomorphism. So it's enough to consider this exact sequence. And the tricky part is to show that this is, we have 0 here. So this is the main ingredient. So, okay. So I have finished my slide. If you want, I can enter into some details, but it's quite hard to describe all the parts. But I'm ready for questions, or if you want, I can try to explain.
Okay, thank you, Marco. So maybe why don't we first see if anybody has any questions up till this point? Hello, everybody, questions?
So I assume the answer is no, but did you consider the topology of the smoothing? So when you smooth the singularity, do you keep the given fundamental group, or might it jump in some way?
I don't know. I think it might jump. So let's go back if you want here. So this is the tricky part of the proof. So we have this degeneration to the normal cone, and we have this base change part. And the description of this can be made using the stuff of derived categories of around the cotangent complex of the map. This is the important things. Sorry. The other part is, the second part is really pure geometric description of this bundle via the dissection. And this is not so easy to describe.
But for example, I mean, like one of the intentions of this is to be able to do the calculations that you were talking about in the previous talk, right?
No, sorry.
Well, I'm saying one of the intentions of this discussion here is to be able to do explicit calculations at the intersection of the two components, for example, in the previous talk, right?
Well, intersection of the, we find again the results of Friedman, more or less. We coincide. Because if we have these two, we have only the smooth part. So it is not a semi-smooth varieties in this, under this assumption, but we can rebuild the Friedman condition. And this is what Mark Green said yesterday. So we have this condition of the normal bundle from one side must be equal to the inverse of the normal bundle of the other side to have so that we have T1 axis coincide with of D. It's simple in this case. In this case, we have no this exact sequence is coincide with the restriction. Here we have 0, so we have to do this.
So Marco, you said something about wanting to give a few more notes or something.
If you want, but it's difficult to explain. Yeah, it was my worry. Yeah, that's why I prepared this talk in a couple of days, just to describe, just to give the idea. It's not so easy because. So if you want, I can try to describe the computation. I don't know if it is helpful. So the main ingredients are this degeneration to the normal cone, and the second ingredient is the computation of the normal bundle in this way. So those are the two main ingredients for the proof. But they are quite technical. So I don't know. Sorry.
I think we might be interested in having just a brief discussion of like how this would be applied in practice. You know, what do you do if you actually have a singularity or a variety and you want to calculate this type of thing?
Yeah, this one. No, I haven't understood the questions.
What do you do? What do you actually do in practice when you want to apply this? I mean, that would be my question.
Yeah, well, we show this theorem that such Godeaux surfaces are smoothable. This is our results. So this is the motivation of our computation, is to prove that Godeaux surfaces built in this way are smoothable. Yeah. So Godeaux surfaces are semi-smooth surfaces, and we have to build the tangent shift and T1 of X in order to study. This is the motivation. This is our application. Main application.
I think Giancarlo has a question in the conversation, which is how do you compute the fundamental group of the general fiber? I think Zonka asked.
We did not compute. Yeah. We did simply try to apply this result of Ciolas. And I have no feeling of what may happen. I think it may jump, but I'm not sure, because it is just a local computation. Yes.
Yeah, there are some surgery. So
we didn't think about the fundamental group.
So is the T1 sheaf actually trivial here, or
no?
So what? Sorry, I missed that.
It's of positive degree.
But it is locally free, right?
It is invertible.
Yeah.
So this T1 of X restricted to D is an invertible sheaf of positive degree.
Oh, but you have some kernel.
We have here some kernel which is supported on the pinch point.
I mean, I think in principle one could try to understand the fundamental group by just looking at the local deformation, what happens to the neighborhood of this elliptic curve D. But first you will have to find out what happens at the pinch points.
Yes. Because this D, in some sense, is the same. We have this elliptic curve. But at the pinch point, we have some shrinking. So this is why it may jump.
Yeah, is it possible that maybe if there's at least one pinch point that then the fundamental group is not going to change? Because I mean I'm not sure about this, but in the case of a curve, you know, the smooth curve has an extra loop, which is the thing where the Dane twist, right? But that's going to sort of be happening along the curve, right? But then if that goes away, if there's a pinch point, maybe that loop sort of becomes trivial. I'm not sure, but I'm wondering whether there might be.
Yeah, that's exactly why I think the fundamental group jump up in this smooth.
Well, yeah, but what I'm saying is maybe it doesn't jump up if you have a pinch point, because that extra loop actually contracts at the pinch point. Maybe, possibly. I mean, if there were no pinch points, then you might have that extra loop, but that's a complete guess.
I'm saying the reverse. So it is possible that such stable surfaces have trivial fundamental group. But if the fiber is
the smooth fiber, you mean?
Yeah, the smooth fiber may have a non-trivial fundamental group. This is just because
maybe
this is just because of what you were saying.
Well, you mean that the pinch point introduces a relation, but it's a finite order relation. It's not.
Yeah.
I see.
Okay. So sorry if it were more quicker talk.
No, that was great. Thank you very much. I'm not sure there's too much of a energy for further computations here. I would perhaps estimate. Okay, so if there's no further discussion or questions or something like that, shall we perhaps wrap up this talk for now? So I thank Marco for stepping in very graciously to take care of this talk too, which was not easy since it was on a short notice. So thank you very much.
Thank you.